Hello friends, welcome back to the CSC Guy. In this video, we are going to discuss some important questions and important points of our first chapter in algorithm design and analysis. So the first question we are going to discuss is the different asymptotic notations. So what are asymptotic notations? Asymptotic notations are used to describe the time and space complexity of an algorithm. There are different types of asymptotic notations. First one is big O notation. We also call it as upper bound. Big O notation is used to describe the upper bound of an algorithm's time or space complexity. It gives an estimate of the maximum amount of time or space an algorithm requires as the input size increases. Suppose we have an algorithm that finds an element in an array of size n by iterating through each element. The time complexity of this algorithm is big O of n because in the worst case it has to iterate through all the n elements. Let's see this example. This is the Python code in which we are iterating n times. In this example, the time complexity is big O of n because the algorithm has to iterate through all n elements in the worst case. Next is big omega notation. We also call it as lower bound. Big omega notation is used to describe the lower bound of an algorithm's time or space complexity. It gives an estimate of the minimum amount of time or space of time or space an algorithm requires as the input size increases. Suppose we have an algorithm that finds the maximum element in an array of size n by iterating through each element. The time complexity of this algorithm is big omega of n because it has to iterate through at least n elements to find the maximum. So this is the Python code for the algorithm. In this example, the time complexity is big omega of n because the algorithm has to iterate through at least n elements to find the maximum. Next is big theta notation. We also call it as tide bound. Big theta notation is used to describe the tide bound of an algorithm's time or space complexity. It gives an estimate of the exact amount of time or space an algorithm requires as the input size increases. So here is an example of Python code in which we are supposing that we have an algorithm that sorts an array of size n using merge sort. The time complexity of this algorithm is theta of n log n because it has to divide the array into two halves recursively and merge them back together. In this example, the time complexity is theta of n log n because the algorithm has to divide the array into two halves recursively and merge them back together. See the code. Fourth is little o notation. We also call it as loose upper bound. Little o notation is used to describe a loose upper bound of an algorithm's time or space complexity. It gives an estimate of the maximum amount of time or space an algorithm requires as the input size increases, but it is not as tight as big O notation. Here, let us suppose we have an algorithm that finds an element in an array of size n by iterating through each element. The time complexity of this algorithm is small o of n square because it is less than n square. You can see the code. Next is little omega notation, loose lower bound. Little omega notation is used to describe a loose lower bound of an algorithm's time or space complexity. It gives an estimate of the minimum amount of time or space an algorithm requires as the input size increases, but it is not as tight as the big omega notation. Let us suppose we have an algorithm that finds the maximum element in an array of size n by iterating through each element. The time complexity of this algorithm is small omega of 1 because it is greater than constant time. So here is a Python code. So the second question. In this, we are going to determine if the equality of 5n square minus 6n is equal to theta of n square. Is it correct or not? In this, we need to check if the function 5n square minus 6n is bounded above and below by n square asymptotically. First, we are going to see upper bound. To show that 5n square minus 6n is bound above by n square, we need to find a constant c such that 5n square minus 6n is less than or equal to c into n square. Dividing both sides by n square, we get 5 minus 6 by n is less than or equal to c. As n approaches infinity, the term minus 6 by n approaches 0. So we can choose c is equal to 5 to satisfy the inequality. Next is lower bound. To show that 5n square minus 6n is bounded below by n square, we need to find a constant d such that d into n square is less than or equal to 5n square minus 6n. Dividing both sides by n square, we get d is less than or equal to 5 minus 6 by n. As n approaches infinity, the term minus 6 by n approaches 0. So we can choose d is equal to 4 to satisfy the inequality. So what is the conclusion? Since we have found constant c and d such that d into n square is less than or equal to 5n square minus 6n, which is less than or equal to c into n square, we can conclude that 5n square minus 6n is equal to theta of n square. So the equality is correct. In general, when dealing with polynomial expressions, we ignore lower order terms and focus on higher order terms, which in this case is n square. The constants 5 and minus 6 do not affect the asymptotic behavior of the function. So we can simplify the expression to theta of n square. Next, we are going to determine if the equality n not equal to big O of n square is correct or not. For this, we need to check if the function n naught is bounded above by n square asymptotically. First, what is Stirling's approximation? We can use Stirling's approximation, which states that n naught equal to root of 2 pi n into n by e power n, where e is the base of the natural logarithm. Upper bound. To show that n naught is bounded above by n square, we can use Stirling's approximation. N naught equal to root of 2 pi n into n by e power n. Since root 2 pi n grows slower than n square, we can ignore it for the purpose of this analysis. We are left with n by e power n. Since e is a constant, we can choose a constant c such that n by e power n is less than or equal to c into n square. Choosing c is equal to 1 by e satisfies the inequality. Conclusion. Since we have found a constant c such that n naught is less than or equal to c into n square, we can conclude that n naught is equal to big O of n square. So the equality is correct. In fact, n naught grows much slower than n square. So we can say that n naught is equal to small o of n square, where small o denotes a lower upper bound. However, statement n naught is equal to big O of n square is still correct, albeit not as tight as possible. It's worth noting that n naught grows extremely rapidly and n square is an extremely loose upper bound. In practice, n naught is often approximated using Stirling's approximation or other methods rather than relying on the loose upper bound provided by n square. Next, we are going to determine if the equality 33n cube plus 4n square is equal to big omega of n cube. is correct or not. For this, we need to check if the function 33n cube plus 4n square is bounded below n cube asymptotically. First, lower one. To show that 33n cube plus 4n square is bounded below by n cube, we need to find a constant d such that d into n cube is less than or equal to 33n cube plus 4n square. Dividing both sides by n cube, we get d is less than or equal to 33 plus 4 by n. As n approaches infinity, the term 4 by n approaches 0. So we can choose d equal to 32 to satisfy the inequality. Conclusion. Since we have found a constant d such that d into n cube is less than or equal to 33n cube plus 4n square, we conclude that 33n cube plus 4n square is equal to big O of n cube. So the equality is correct. In fact, 33n cube plus 4n square grows exactly like n cube asymptotically. So we can say that 33n cube plus 4n square is equal to theta of n cube, where theta denotes a tight bond. The term 4n square is dominated by the n cube term as n grows large, so we can ignore it for the purpose of this analysis. The leading term 33n cube determines the asymptotic behavior of the function, which is sigma of omega of n cube. Next, we are going to determine if sigma I from 0 to n t square is equal to theta of n cube. Is this equality correct or not? The equality is not correct in general. The summation sigma of t square from 0 to n, I equal to 0 to n, can be evaluated as t square plus t square n plus 1 times is equal to n plus 1 into t square. Since t is a constant, the summation grows linearly with n, not cubically. Therefore, the correct asymptotic bound would be sigma of t square is equal to theta of n, not theta of n cube. However, if t is a function of n, such as t is equal to n, then the summation would be theta square plus 1 square, 0 square plus 1 square plus 2 square and so on n square. This summation is known to have a closed form solution. N into n plus 1 into 2n plus 1 by 6 will be the sum of this, which grows cubically with n. So in this case, sigma of I equal to 0 to n I square is equal to theta of n cube. But this is a specific case, and the original equality sigma of t square 0 to n is not correct in general when t is a constant. When t is equal to I, then it can be theta of n cube. Next, let us discuss an algorithm for selection sort and compute its time complexity. So let us first discuss algorithm for a selection sort. In this, what is the input we are taking? We are taking an array A of n elements. Next, what is the output? The sorted array A in ascending order. Next, we have three main steps. First is initialize I to 0. Next, step 2, repeat until I reaches n minus 1. In this, in the second step, we find the minimum element in the unsorted portion of the array A of I to n minus 1. Let min I be the index of the minimum element. Next, in step 2, we swap the element at the index I with the element at index minimum I. Next, we increment I by 1. Step 3, we return the sorted array. Here is a Python code which illustrates this algorithm. Next, let us analyze time complexity for the let us compute time complexity for this selection sort. In this first term is big O of 1, which is constant time. Second step, this step is repeated n minus 1 times. In each iteration we perform the following operation. In second step, first thing we do is finding the minimum element in the unsorted portion of the array. It takes big O of n minus I time, since we need to iterate over the n minus I elements. Next, in second step, we do swapping of two elements. It takes big O of 1 time. Next is, in second step, we increment I, which takes big O of 1 time. Total time for step 2 is big O of n minus I plus big O of 1 plus big O of 1, which equals to big O of n minus I. In step 3, which we are returning the sorted array, it takes constant time big O of 1. Since step 2 is repeated n minus 1 times, the total time complexity of selection sort is big O of n minus 1 into big O of n minus I, which equals to big O of n square. Therefore, the time complexity of selection sort is big O of n square. Note that this is an upper bound and the actual running time may be less for certain inputs. However, in the worst case, selection sort has a quadratic time complexity. Next, we are going to discuss some important points. First is, we are going to define an algorithm. What is an algorithm? It is a well-defined procedure that takes some input, processes it, and produces a corresponding output, typically in a finite number of steps. Second important point, what is the time complexity? It is a measure of the amount of computational time an algorithm requires to complete, usually expressed as a function of the size of the input, typically denoted as n. Third important point, what is profiling? Profiling is the process of measuring and analyzing the performance and resource usage of a program or system, often with the goal of identifying bottlenecks and optimizing efficiency. Fourth important point, how to validate algorithms. We validate algorithms by verifying the correctness of an algorithm by testing it with a variety of inputs, including edge cases, and comparing the output with the expected results, often using techniques like unit testing, integration testing, and stress testing. Fifth important point, how to devise algorithms. For devising algorithms, we develop a step-by-step procedure to solve a problem by breaking it down into smaller subproblems, identifying patterns and relationships, and using techniques like divide and conquer, dynamic programming, and greedy approaches to create an efficient and effective solution. Sixth important point, how to analyze algorithms. For analyzing algorithms, we evaluate the performance of an algorithm by determining its time complexity, example big O of n, big O of n log n, and space complexity, and accessing its scalability, efficiency, and trade-offs using techniques like big O notation and asymptotic analysis. Seventh important point, how to test a program. Testing a program, we verify the correctness and reliability of a program by executing it with a variety of inputs, including normal, boundary, and erroneous cases, and checking its output against expected results using techniques like unit testing, integration testing, and debugging. Eighth important point, find the time complexity of conventional matrix multiplication algorithm. The time complexity of the conventional matrix multiplication algorithm is big O of n cube, where n is the number of rows or columns of the matrices being multiplied. The algorithm involves three nested loops. Two loops to iterate over the rows and columns of the matrices, and a third loop to perform the dot product of the row and column vectors. Each iteration of the innermost loop performs a constant amount of work, that is, a multiplication and an addition. Since there are three nested loops, each iterating n times, the total number of operation is proportional to n cube. Ninth important point. What is space complexity? It measures the amount of memory or storage required by an algorithm to execute, typically expressed as a function of the input size, big O of 1, big O of n, big O of n square, indicating how much space is needed to store data structures, variables, and other information during execution. 10th important point. What is big omega notation? It represents the lower bound of an algorithm's time or space complexity, indicating the minimum amount of time or space required by the algorithm, providing a guaranteed performance threshold. Next important point is little o notation. What is little o notation? It represents an upper bound of an algorithm's time or space complexity, indicating that the algorithm's performance grows asymptotically slower than the given function, providing an upper limit on the resources required. Next important thing to discuss is listing important problem types. Some of the important problem types in computer science and algorithms design is sorting algorithms, searching algorithms, graph problems, dynamic programming, backtracking algorithms, greedy algorithms, string algorithms, bit manipulation, etc.